attempting the lab session 1, you need to go to my GitHub repository. The link will be given to you in your student companion guide. Here you go to the repository section, and there you will find hardware software co-design labs. So I updated this 1 minute ago, and you can just click on this IPython notebook. As you open the notebook, so before you actually attempt any it, just make sure to star it and click on watch, so that any changes which I make, you are able to actually identify that, and it's notified to you. So make an account on GitHub and log into that. It's really good. Any changes which people suggest or which I feel the code is not going right, and for this lab session it's not that relevant, but for future lab sessions the code bases will be huge, so you might be requiring that. So this is the IPython notebook, and you need to attempt this, understand the code of it. I'll walk you through this briefly, but what you need to do is click on open in Colab, and this is where it will lead you to. Okay, so first of all, click on connect to a hosted runtime, and click on change runtime type and choose this to T4 GPU, because we want to run this on GPU. So let's just wait for it to get connected. Okay, so after a few seconds it's connected to the resources, and the system RAM you can see, and the disk which it is occupying. So Jupyter Notebook is actually comprised of certain markdown language and certain code sections. So I'll just briefly introduce you. So this is an introduction to PyTorch tutorial. Sorry, my image is blocking it, but you might be able to see it that from this point onwards. Welcome to the comprehensive PyTorch tutorial. In this notebook, we'll explore the fundamentals of PyTorch, one of the most popular deep learning frameworks. Most of the code which we'll see later on in our course, that will also be based on PyTorch, and I'll quickly show you also if possible. In fact, towards the end of the lab session, I'll show it to you. I'm not going to go through the entire code. This is a self-paced thing which you have to learn and understand it yourself. So just a second. All right. So it's for those who have some programming experience, which I hope most of you have, and a basic understanding of machine learning concepts that you might have received through the initial first week and some lectures. All right, so let's start up. We'll begin with installing Torch Vision. There is an N here, please delete that before running. So control and backslash button is used to comment and comment. You can click on run anywhere. And this will download all the necessary files required for Torch and Torch Vision. All these NVIDIA CUDA libraries, runtime, CU12 libraries, CU solver, CU parser. We'll be looking we'll be also in some of the future lab sessions, we'll be looking at that also when we do the GPU programming section. So shift plus enter is what we use to run it. You can also manually click on this button to run it. And let's just see whether our PyTorch is installed properly or not, and let's try to print the PyTorch version. Okay, so it has successfully printed the PyTorch version, just 2.3.1, and now we've imported the libraries. Now we'll first of all look into tensors. The tensors are the building blocks of PyTorch. Tensors are the fundamental data structures in PyTorch, and they are similar to NumPy arrays, but can also be used on GPUs to accelerate computing. So let's explore tensors. Creating tensors, so we can create them using Python lists or tuples. So let me zoom in a little bit, and so let's see that here we have creating a 1D tensor and creating a 2D tensor, and I hope you can see the display on the screen. So 1D tensor 1, 2, 3, 4 can be initialized like this, and this is row by row we're entering. So first row, second row, third row, and these are the column elements. So the command for importing them is simple torch dot tensor, and then inside the brackets you pass in the tensor which you want. So it's as simple as that, and here if it's a 2D array, then you can do it something like this. Next, using PyTorch functions. So just like that, you can create torch.ones. So this here you enter the rows and columns, and you can print the ones tensor, you can create a zeros tensor, and you can create a random tensor as well using torch.rand. So from numpy arrays, how you can do, there's an np.array if you have imported. So numpy also we've imported in the starting in the code itself, and you can do np.array, and from that you can call the torch library torch.from numpy, and you can pass in the numpy array, and then if you print the tensor from numpy array, this is the variable name, so it will print out that tensor. So what are the properties, how to define the properties, because that's what we'll be requiring every now and then to calculate that what is the shape, the data type, and the device where it is running, right? So let's keep on simultaneously running this as well. Shift enter is what we'll choose to run these codes. We have not allocated right now this to the GPU, so it's printing device as CPU, which is understood. We'll do that later. And for basic calculations, doing it on CPU is also fine. There are no issues with that. So tensor.shape, tensor.data type, you see all of them are float 32 right now, and .device is CPU. Some tensor operations which we can do is addition, subtraction, multiplication, division. Very simply, it's element by element. Addition and multiplication, all these are element wise operations. So if there are certain matrix operations, like we have to matrix multiplication, then we can choose torch.matmul operation with M1 and M2 passing the matrices. Always make sure that the dimensions of these are matching, and we can do element wise using M1 into M2 as we had done above. There is a special operation called slicing. So based on that, we can choose the operation which we want. So here we had just like we had printed the array, like we had to do the print tensor. So if we do the print tensor here, and so this is 1 2 3 4 5 6 7 8 9. If you have to select the first row, so that can be indexed simply using this 0 thing here. So I'll just take out the pen to explain you. So if you do this 0 operation, then it will select this whole row 1 2 3, it will select. If you want to print the second column as in 2 5 8, this is what we want to print, then what we need to do is do operation like this. So how we understand this, if we place in colon, it means select all rows, basically the first element, and out of that from every row choose the first element, and this using this construct the whole thing. So this is known as slicing operators. It's quite commonly used to pick up certain elements. So from all the rows, basically 1 2 3 4 5 6 7 8 9, from every row it will pick up the first element. So this is the 0th element, this is the second element, this is the first element. So this is what this operation will do. And if you want a submatrix, so starting from 1 to end, so starting from first column up to the last column, so this starting from, so this signifies the row. So starting from first, this is the 0th, first, second, third in that language, or 0th, first, second. So starting from here 4 5 6 7 8 9, out of that choose the columns 5 6 8 9. So therefore it is choosing this 5 6 8 9. I hope this is clear. It will become more clear when you practice it. Okay, so we can do tensor reshaping as well. We can reshape the tensors to different sizes. So we can do tensor.reshape 2,3. So we can see this reshape tensor. We can flatten out a reshape tensor using the dot flatten operator. That also we can do. And we can convert a tensor to numpy using tensor.numpy, or just pass in the numpy and it will convert to a numpy array. So this is a numpy array and this is a PyTorch tensor. There are certain visualization things which you can see, like if you want to plot the tensor, and we'll pass in this tensor and the title which you want. So here we have initialized a random tensor of size 10 comma 10, which you can see here, and we'll pass this function visualize tensor and this random 2D array along with the title. So using plt.figure, so plt we have imported again on the top, you can see here. So why am I spending so much time? Actually, it's because just so that all of us are on the same plane, or else you can follow it along as well. I'm just giving you an introduction of how to read the Pythonic kind of a code. So figure size we're mentioning here, you can change this as per your variation, and we're doing the IM show for showing it as an image, and we're passing this tensor.numpy, and we're giving this cmap BDDS along with the color bar and the title. We're displaying the title as the title, and then using plt.show it is putting this structure. So same thing, you can see that if we have a structured 2D, so this is a random 2D array and this is the color map which we have. Now this in the same color map, in the same color map, but if it's a structured array, like gradually see it's changing from the highest value to the lowest value. So, and remember, this is what we had seen in the AlexNet activations, if you remember the first lecture. This is what we were seeing actually, that what is the value of that weight and that activation. So we're creating a range from 0 to 100 and then reshaping it as a 10 cross 10 tensor, not like just a random 10 cross 10, it's a structured tensor. So these visualizations help us understand the values and patterns in our tensors, which can be partially useful when working with image data or weight matrices and neural networks. So conclusion of the tensor section is that we know how to create tensors, tensor properties, basic operations, reshaping, converting between tensor and numpy, and some visualizations. And these are the foundation of all computations in PyTorch. As we move forward, we'll see how to use these concepts to build and train neural networks. So first thing we'll understand is the linear regression. Before working on some deep learning thing, we'll just do a simple linear regression, and we'll create a model, train it, and visualize the results using PyTorch. So let's create some synthetic data following this y equal to mx plus c. So epsilon is a random noise. So what we want to predict is this y equal to mx plus c, but the data points will lie in this epsilon, some random noise we've introduced. So we set a manual seed so that each time it is reproducible. 42 is a very useful number because there was a movie called Hitchhiker's Guide to Galaxy in which the answer to the universe was 42, which made not much sense, but that's how 42 is holding a significant is of significance, and it's a seed, and the same seed we're providing to the NPs random so that results are reproducible. We generate on the x-axis a linearly spaced line from 0 to 10, and we are taking almost 100 points in that. So linearly spaced, this torch.linspace is giving you that, and y equal to mx plus c. So here m is 2 and this is c, and we are introducing a randomness with scale 0.5. So we reshape x and y for PyTorch. So x and y is reshaped, and then we visualize it. So it's the same, we give it a figure size and we do a scatter plot where in the x-axis there is x, so that's linearly spaced data, and on the y we have this thing plotted, and we give the synthetic data for linear regression, and this is how we have generated the data. So now what about creating a linear model? So now let's begin a simple linear model using PyTorch nn.module. So here you'll just have to be careful of the syntax which we are using, and things will be clear to you. So import from torch.nn as nn. So this is how you begin, and we are creating a linear regression model. So the standard way of doing that is just whatever model type you're creating, you create a class of that linear regression model which we mentioned, and we pass in this nn.module to it. So this is the first part, And inside this we have a constructor in which so some hints of object oriented programming and just follow along and use ChatGPT to understand things better. But here we're just initializing the super vector, which is from which this class is imported, and we're defining one input feature, one output using self.linear here. The input feature which we are choosing is x, and the one output which we have is y, and the forward pass is nothing but we just have to return self.linear x. So linear is a class because we're making linear model, therefore linear x. Later on when we do convolution operations, you will see that this thing here will change. So this is how we define them forward part. Given an x, we'll just calculate the linear of x and return that. So we call this linear regression model, that is we create an object of this class and call it model, and we print the model. So you see that the linear regression model is printed with linear in features as 1, out features as 1, bias as true. So now defining loss function and optimizer. So for linear regression, we use mean squared as our loss function and SGD as our optimizer. We haven't discussed much about loss function, stochastic gradient descent, and what the optimization is. But these are like what is used to train the weights which we will be initializing. So that is where it is used in training. So we have done MSC loss, nn.msc loss as our criteria, and our optimizer is SGD, and we've passed in model.parameters with learning rate as 0.01. So let's actually better than explaining this would be to run it and show you. So here is our synthetic data, and here is the definition of model. Here we're defining the criteria and the optimizer, and inside the training loop we're training it. So here the things is getting trained very fast because it's just a very simple thing which we are training. So how we have started to train? So we are training the whole thing about 100 times, and for each time we go in the forward direction, we predict based on the model. So in this model we pass on the x. So here you see that we had created the model, linear regression model, and inside that we have passed x, so it will predict a y. We compute the loss function using the y which was our any random noise y, this y, and the predicted y, and that is how we compute the loss. So the criterion which we had set, this criterion, we choose this criteria and to calculate the loss function, and we append the loss item in the losses. This we are making as losses so that we can plot it in the end, and then we choose to do the backward pass and optimize the step. So after calculating the loss function, we do the back propagation step. Here we have optimizer.0grad, we do loss.backward and optimizer.step. So all this will actually do the backward pass and do the optimization step, and at every 10 epochs we want to print the epoch and the loss. So here you can see the loss is continuously decreasing, which is something what we want. And finally when it is all over, we want to print the model parameters. So model.linear.weight.item, we are printing that up to 4 decimal figures, and bias item we are printing again up to 4 figures. So this linear thing, the class we have defined here, the linear class, that itself has defined 2 parameters, mx plus c. So therefore we are able to get this out of that. Things might not be that obvious because we have initialized the super thing, but this is how machine learning in PyTorch works actually, that the class is imported from the higher class. So therefore we are getting this model.linear.weight item and not bias. That is what we are printing here. So you can go through the detailed example of how we're doing it, setting up the loop, calculating the forward pass, computing the loss function, and doing the backward pass and optimization. and some mathematics is also included. So therefore this is how we're doing it, and then you can visualize the results. So you can see that the linear regression results. So this is what we've predicted, and the training loss has decreased over time, over the epochs, over the 100 epochs. And this is how you can make prediction based on the data set. So now PyTorch workflow with complex data set. So again, this is a little more complex data set, and we're defining a machine learning model. So you can try and run this data set. So this is just to give you an intuitive idea and intuitive example, and try to actually run it and see the see how it is flowing, because later on we'll see that most of the models which we are going to use on our FPGA are based on PyTorch only. So it's a good thing that you have an idea of how it's working. So here we have defined the forward pass, and we have introduced some non-linearity now, because the data set we have to train on is non-linear. So it's when you pass x, so x goes to the self.layer1 x, and the layer 1 which you are defining is a linear layer from inputs 2 to output 16, and then from 16 to 8, and from 8 to 1, and the ReLU layer we are defining as this nn.ReLU. So this is how we are doing it. The first thing is giving it to layer 1 and then applying activation function on it, then giving it to layer 2, applying the activation function on it, and then the layer 3 and applying a sigmoid function on it. So this is how the model which we have looks like. There will be two features in the first layer which are going as input, and output would be 16. Obviously whatever is the output in layer 1, that will be the input in layer 2. Output of layer 2 will be the input of layer 3. That is how we have defined. And the ReLU and sigmoid. So this is the criterion optimizer which we are choosing this time is Adam optimizer. And binary cross entropy loss, there are multiple kinds of loss functions we had seen in the first class, suitable binary classifications, and output is wherever the output is either yes or no, 0 or 1, that is where binary cross entropy works the best. So as we train the neural network with each epoch, so number of epochs is 100, we're storing the losses in this list, and the same as before, forward pass, the backward pass, and the optimization step, and at the end of this training loop we'll get the training loss, and if we do the evaluation of the model right now, then the accuracy comes out to be 98.3%. and visualizing the decision boundaries, so this is the code which you can use for visualization. So this is how it will look like. And now comes the neural network for classification part. So this is a little more complicated. We're loading the iris data set, and this is a custom data set for iris which we're creating here. We'll build the neural network again, fully connected layers which we had studied, and again the same step of training the model. So training loss is decreasing and the training accuracy is increasing, and we'll do the evaluation. So in evaluation there are multiple matrices which we can draw, like the true and the predicted, how it is varying, and we can just predict like what the sample 1 is predicted as a setosa and the sample 2 is predicted as a virginica. So all these things you can do. And finally image classification with convolution neural network. So before that it was a fully connected layer, now doing it with the convolution. So here we are trying to do it on a GPU because convolutions require a GPU. So you can you can go through some key points and visualizing the data, and this is the data set which we have. So certain images of 8, 9, 6, 4, 0, 1, 3 and 6, 8, 0, all these are printed here along with how it is looking like. So we've chosen to display the image using IM shown, And then how the neural network architecture is defined. So this is a convolution neural network. So here we have defined definitely like class net we are defining, and we're sending it to the device, which is CPU in our case. It can be GPU as well. Here what we're doing is we're importing the init, like the super net class we have. We're importing the constructor from that, so it will give us all the presets which are required. Then we're defining the first layer of convolution 2D as 1,32, and kernel size we're keeping as 3 with padding as 1. So previously we had like 3 channels RGB. Here we just have a single channel, so therefore this one is representing that. And this 32 is representing how many output channels we have. So definitely the kernel size 3 is 3 cross 3 we are choosing, and this is how we're in the second convolution layer we're defining 32 to 64 mapping. Then we're choosing a 2D max pooling. Remember, max pooling is used for downsampling, so we're downsampling this and then finally passing it to a fully connected layer. And ultimately you can see that the second fully connected layer is mapping it to 10 outputs. Here we are getting from 128, we're mapping it down to 10. Before that we had to flatten it out. So for flattening, the input size which would be taken is this 64, and we'll deliberately change the view of X from any matrix to a 64 cross 7 cross 7, and this is what we'll pass into the fully connected layer 1. So this is the final how the neural network is looking like. We again do the same kind of criterion and optimize it, training the loops, and we're training it, and finally we're printing these losses and accuracy. And as you can see, the confusion matrix of the 10 classes which we have defined, it is, confusion matrix is important metric, important way on how to see that how many it is predicted right, how many it is predicted wrong. So, and what classes, like the first class, how many times it has marked it as the 6th class. So you can see it has 3 times here, it has done that. And then just visualizing the predictions. So you can just call the visualize predictions, and here you can send it the model along with the test loader data. So here you can see that it is predicting, it is taking in the images and predicting it appropriately. So try to run this whole notebook. This will give you a good introduction of the PyTorch. So one last thing before we end this recording is that I want to show you that why we are doing all this. So when we go to Vitus AI documentation, and we head over to this documentation here, let's choose anything, it will not matter, and we head over to the Vitus AI model zoom. You can see Vitus AI library can performance table online. So now this is a table which the people have, the designing CMD people have made, and you can see that out of this, in the framework, PyTorch framework, so many of it is available. So many of these models we can directly use and run our code on. So many of them belong to image classification, and some of them for depth estimation, and some of them for natural language processing, object detection. All these are different things, and the model architecture which they have chosen, that also they have mentioned ResNet 50 or whatever it is. Along with that, the research publication which is used to make this model, and the data set which they have used, the URL of the data set, the input dimensions of the image, and the floating point accuracy, the quantized accuracy. So I hope you're getting the sense of the number of operations, the giga operations ops which is there, the percentage pruned model, and the different FPGA boards, and how, at what frequency they are running, and what is the FPS which they are giving. So many of these models we can directly download and can just run and benchmark at a place. So that's why it's important we get a good understanding of PyTorch, which is used for most of the research purposes. So thank you so much.